Okay, so this is example 2 in section 12.9, and we're going to use change of variables and the Jacobian to calculate this double integral. And if we look at the original double integral, and if we just think about trying to find the antiderivative in terms of x or in terms of y, that would be nearly impossible, at least with the techniques that we have. So this antiderivative, since it is not possible, really is going to be more manageable with the Jacobian. Unlike the first example or the warm-up, when we're looking at the Jacobian here, u and v are not given to us. And so we have to come up with sort of a creative way to identify a change of variables that makes sense and helps us. And this takes a little bit of practice, but essentially when we look at the problem, we look at the inside of this cosine function, we want to think of something that we can assign so that the antiderivative is possible in terms of u and v. And one option would be to let u equal y minus x and v equal y plus x. And if we think about cosine of u divided by v, and if we did the antiderivative, that would be much more manageable than how it's written in x and y. You'll see in a moment how that works. Okay, now our goal, what we need to find is an equation x of u v and an equation y of u v. So what we're going to need to do is rearrange this and get an equation x equals u's and v's and y equals u's and v's. And right now, it's not written that way. So let's start by maybe taking this one, and we could solve for y, which gives us v minus x. And if we use then this equation and we plug in what we have here, v minus x for y, we get v minus x, which gives us u equals v minus 2x. And if we solve that one for x, we have, let's see, we either have v minus u over 2, or maybe it's easier to write this as 1/2 v minus 1/2 u. So there you go. That's our equation for x in terms of u and v. And then we also have to do the same thing for y. So maybe let's take the first equation we have here, and we'll solve this one for x. So we have x equals u plus y. Nope, sorry, let's see. We'll have x equals y minus u. And then we'll plug that one in to the other equation for x. So what we get then is, let's see, so v equals y plus, instead of x, we have y minus u. So that gives us v equals 2y minus u. And if we solve that for y, we would get v plus u divided by 2. Or maybe a better way to write it is 1/2 v plus 1/2 u. So there we go. We got our two equations. So in example 1, these were given to us. In example 2, we had to create them. This is not the only option, but this option should work. Okay, now our next task is to find the Jacobian. So maybe we can label it as 1. So we're looking for the Jacobian, and the Jacobian formula is given to us in the first page of this section. And again, one of the ways to remember it is to use this this matrix. All right, so now we have our equations. We got, let's see, we got the partial of x with respect to u is negative 1/2, and with respect to v is positive 1/2, and y with respect to u is 1/2, and with respect to v is also 1/2. So that gives us negative 1/4 minus negative 1/4, which is negative 1/2. All right, so that's our Jacobian. Okay, the second thing that we did, modeled after example 1, was that we changed our variables. So the original double integral over r is cosine of y minus x divided by y plus x. And we're now going to change this into the double integral, and we can call it a different region. Let's call it S of cosine of u v, u divided by v. Now, if we think about if we were to do the antiderivative of this, we would want to do the antiderivative with respect to u first before v. So we would want to do this as du dv. If we did it with respect to v first, that'd be pretty tricky. Now we're also, I should have added this in, we're going to multiply by the absolute value of the Jacobian. So we're going to multiply by 1/2. And there we go. That's going to be our change of variables. Okay, so step 3 is that we want to draw out these regions. The original region in terms of x and y, we have vertices at, let's see, 1, 0, and 2, 0, and 0, 2, and 0, 1. And so what we have is this sort of sideways trapezoid looking thing. And so what we're going to do is try to figure out how to put this, or how to draw this in the UV plane. All right, so let's start with our equations. So this one is going to be y equals 2 minus x, and this one is y equals 1 minus x, and then that horizontal is, of course, y equals 0. This one is x equals 0. Okay, so what we're going to do is transform this, and what we did in example 1 was just sort of make a little table here. So if that's helpful, you can certainly do that. So we have our original. Let's start with x equals 0. So if x is equal to 0, x is the same thing as 1/2 v minus 1/2 u, and then so that's equal to 0, which that would imply that v is equal to u. So we have v equals u, which is the transformation of x equals 0. And then if we just kind of go in order here, we have y equals 2 minus x, and we can substitute in y, which is 1/2 v plus 1/2 u equals 2 minus the quantity 1/2 v minus 1/2 u. Let's see if we just rearrange this a little bit. Okay, so balance it out. The 1/2 u's will cancel. We can combine the v's together, and this would give us, let's see, v equal to 2. So there we go. The next one, y equals 0. So we have y, which is 1/2 v plus 1/2 u equal to 0. That would imply that v is equal to negative u. And then the last one is y equal to 1 minus x. So we have 1/2 v plus 1/2 u. You can see that this is just a large, ugly system of equations. All right, so this one, again, if we distribute and balance, we have a similar situation to that second equation we did. So we'll have v equals 1. Okay, so we have 4 equations that we're going to transform. So v equal to u is going to be, let's see, let me change this axis a little bit. Okay, so we have v equal to u, and then we have v equal to negative u. This isn't the best sketch, but then we have v equal to 2, which let's say that's about right here, and v equal to negative, or to positive 1. V is equal to 1. So there we go. So here's our region. And you might think to yourself, well, how did we just simplify this? But the original Well, number one, the original integrand cosine of y minus x divided by y plus x, the antiderivative is really difficult to do. So that was one issue we had. But then the second issue, if you look at the region here with x and y, and if you think about taking this particular region and setting it up as a right minus left or a upper minus lower and that kind of thing, the region becomes a little bit tricky because, for instance, let's say we do like an upper minus a lower. This particular function is the upper graph, but the lower one changes. So, for instance, this is the lower function until x is 1, but then the lower function changes, which means that we would have to do, similar to what we did in the warm-up, we would have to have two different double integrals, which just takes a lot of time. So if we look at our new region, even though it looks kind of complicated, it actually is better for us because there's one distinct upper function, one lower function. There is a distinct left function and a distinct right function. There isn't a separation that needs to occur. So we can do this with one double integral versus multiple double integrals. Okay, so let's take this and set up what our double integral should be. So our fourth step, we know that we have the change of variables. That I'm going to pull that 1/2 out. And then we have the double integral of cosine of u divided by v. And remember, we talked about how we want to do this using the order du dv versus dv du. So with u, u has a function, and I'll refer to the graph up here. So the function on the left is v equals negative u. That's the function on the left. So that's going to be the lower function, which we're going to write as u equal to negative v. Then there's a function on the right side, which is this one, and that's going to be v equal to u. So this integral has a lower limit of u equal to negative v and an upper limit of u equal to v. And again, that's going to border our region up here, left to right. Then we have v, and v is constant, so the lowest v is 1 and the highest v is 2, so the outside integral is going to be 1 to 2. So there we go, we finally have our setup, and now it's just a matter of calculating this antiderivative. So I'll pause and write some of this out. Okay, so here's our first set. So we have the antiderivative. Remember that u is the variable and v is the constant, so this v shows up because it's the antiderivative. That's basically a u substitution, but it's kind of the anti-chain rule, more or less. We plug in our limits and we get all this stuff. So one thing that will actually help us here is that remember that sine of x is an odd function, and because of that, sine of negative 1 is equal to negative sine of positive 1. And that's going to help us with simplification here. So in other words, what we have is 1/2 times the integral of 1 to 2 of v sine of 1 plus v sine of 1 dv. That gives us 2 of those. So I won't skip any steps here. So we have 2v sine of 1. And remember, sine of 1 is a number. So this integral then is 1/2 times 2, which is just 1. Sine of 1 is our constant from 1 to 2 of v dv. And that gives us sine of 1 times 1/2 v squared, evaluated from 1 to 2. So we have sine of 1 times 2 minus sine of 1 times 1/2. So we have 2 minus 1/2. So our answer here is 3/2 sine of 1.